Welcome. I am Karen McFarland, the punk rock professor, here to give you clear and concise tools to help you crush chemistry old school style. Just me, whiteboard. Let's get going. I want to talk today about the Henderson-Hasselbalch equation and how it applies to blood chemistry, specifically looking at the pH of our blood. Our blood needs to stay very close to a pH of 7.4. So there needs to be a lot of intricate systems going on chemically in our blood to help our physiology maintain that pH. So let's talk about the few buffering systems that there are. There's definitely more than one because there's a lot going on in our blood and we've got to stay in that realm of 7.4 to stay alive, all right? So we've got amino acids in our blood. We have tripeptides floating around, we have proteins floating around. All of those have amino acids that play a role of buffering our blood. We also have a phosphate buffering system. In addition, this is the one I want to focus on, we have carbonic acid and bicarbonate working together as a buffer to help maintain our blood chemistry. So let's take a look at that specific equilibrium and then apply the Henderson-Hasselbalch equation to it. Okay, so in terms of bicarbonate and its conjugate acid, carbonic acid. Okay, so let's look at this equation here where we consider carbonic acid in equilibrium with hydrogen ions, losing that hydrogen ion, and bicarbonate. All right, so we have these species in our blood. Bicarbonate might sound familiar. Baking soda is sodium bicarbonate, okay? So this equilibrium is occurring in our blood, and these are the two components of the buffer that I want to talk about. Now let's look at the Henderson-Hasselbalch equation. So Henderson-Hasselbalch, you may want to watch the video that talks more specifically about the Henderson-Hasselbalch equation, but as a reminder, and let's look at it here, the pH of a buffer will be equal to the pKa of the weak acid, in this case carbonic acid, plus a ratio of the conjugate base over the conjugate acid. In this case, bicarbonate over carbonic acid. Base 10 log of the bicarbonate over carbonic acid. Okay, so we know that in blood we must maintain pH of 7.4. So let's put that in as our target pH. All right, at 37 degrees Celsius, that's body temperature in Celsius. The pKa of our weak acid, of our carbonic acid, is 6.1. Okay, so that is a known value at body temperature. Okay, so what that means is that we could actually calculate what the ratio is of bicarbonate over carbonic acid. We know this value, we could figure out what that ratio is. So that is going to be something that is known, and it turns out that it has a value of about 20. Okay, what does that mean? 20. Okay, let's think of the significance of that. What it means is that we have this ratio here that is 20 to 1. Okay, so I'm going to use a different color so we can really focus in on this. This means that our ratio right here is 20 to 1. For every 20 of these bicarbonate ions, we only have one of the carbonic acids. Okay, that's fine. Again, what does it mean? All right, so to really understand what's going on, we need to invoke another equilibrium. All right, so let's take a look at carbonic acid and what else it can do. So I'm going to write up another equilibrium. Let's write it down below here. I'm going to put carbonic acid in the middle. Carbonic acid can do a couple things. One of them we already acknowledged. It can lose a hydrogen ion. Okay, and we get the bicarbonate. All right, this is what we have already written up here. But it can also undergo another equilibrium, and that has to do with water and carbon dioxide. Okay, so water and carbon dioxide. Here, these other species are all in aqueous solution. Water is liquid, carbon dioxide is a gas. Okay, so now let's think about this 20-to-1 ratio. All right, this 20-to-1 ratio. This is where I was saying, all right, the ratio between this and this is 20-to-1. We have oh wait, I wrote that backwards. Let me erase. Thank you. Okay, 20-to-1. We have a heck of a lot more of the bicarbonate than we do of our carbonic acid. So that means that this carbonic acid needs to be depleted somehow. The physiology in our body needs to be constantly getting rid of or reducing the concentration of the carbonic acid. This needs to be a constant ongoing process if we think about this equilibrium up here. And if we think about weak acids and the behavior of weak acids. What do we know about weak acids? And again, you watch the video I made about weak acids, where weak acids are mostly staying together as a molecule. And just a few of them are breaking apart to give the hydrogen ions and the conjugate base. Mostly staying together as the acid. Check it out. We have to maintain this ratio where it's mostly the base, not the acid. Okay, so that's where something else needs to be going on. We need to be drawing away. If we think about Le Chatelier's principle, if you're familiar with that, somehow we need to be drawing away concentration of carbonic acid. How could we do that? Oh, if only there was a way that we could just get rid of carbon dioxide. If only there was a way. Yes? Exhaling. Through our breathing process, we are exhaling. We are getting rid of carbon dioxide. We're driving this equilibrium this way. We're maintaining a low concentration of carbonic acid, thereby achieving this ratio of bicarbonate to carbonic acid, thereby maintaining a pH of 7.4. Ta-da! Our bodies are amazing. Chemistry is amazing. Henderson-Hasselbalch equation is amazing. I love it. You know what else is amazing? L7. That's right. It is time for a bonus track where I'll give you a tune to listen to. L7, I've got to say, this band is the band that made me pick up a guitar back in 1990. I just wanted to rock out. If I could ever rock out as hard as they did, I would be so happy. And I can say that I have. And thank you, L7. So pull up their record, Smell the Magic, from 1990, L7, and listen to Shove. You will not be disappointed. So thank you so much for listening. Like and subscribe if this has helped you at all. I love doing this. And cheers. I will see you next time.